Okay, welcome back. Hope you had a nice little break. Yeah, like I said, now we're going to go through the different types of disturbances that can be elicited on a system that is at equilibrium. First of all, we can do a concentration disturbance. Hello, Hazel. She's prowling about this morning. We can have a concentration change. We can have a volume, a pressure change, and we can have a temperature change. Okay, so these are the three ways that we can disturb an equilibrium. So let's talk about concentration change first. What happens when we disturb an equilibrium by changing the concentration of one of the species involved? For example, let's look at a reaction between N2O4 decomposing into NO2 gas. Sorry, this is a gas, I should write. If we add in, say, we add in some NO2, okay, we're adding in NO2, this will force the reaction to shift in this direction. And this happens because there's excess NO2, there's more nitrogen dioxide than there was in the equilibrium. So now the concentration of nitrogen dioxide is imbalanced with the concentration of N2O4, and therefore it must create N2O4 to again balance this system out. Okay, so if you think about it, before you add anything into this reaction, Q, our reaction quotient, is equal to K. After you add in, the products are now much higher than the reactants, right? So we've increased the concentration of NO2, has gone up. That means that Q now is greater than K. Okay, we've increased the number of products in that quotient, which means that Q now must therefore be greater than K. And what happens is the reaction therefore shifts back left. The reaction shifts left until Q is equal to K again. Okay, so it's always going to re-equilibrate itself no matter what you do. So when you change the equilibrium, when you disturb the equilibrium, by changing the concentration, the important thing to look at is the relationship between Q and K. When Q does not equal to K, the system will re-equilibrate itself so that Q is equal to K again. And just think about what Q actually means: products over reactants. So if you add more products into the problem, Q is going to be greater than K, and so it's always going to shift left. Now, if you take away products, or if you add in reactants, that means that Q will be less than K because you're dividing by a higher quantity. And because of this, it's going to shift to the right. It's going to shift towards the products. Okay. So let's just write that out in explicitly. So the opposite happens if we add in N2O4. Okay, Q in this case is less than K because you're dividing by a larger number. You're dividing by the reactants. Therefore, the reaction shifts. The reaction shifts to the right to compensate until Q is equal to K. Okay. Let's look at this or how this looks in graph world. So if we have concentration on the y-axis and we have time on the x-axis, let's say we have some equilibrium concentration of, these are bad straight lines. Let's see if we can do that better. Equilibrium concentration of NO2 and N2O4. Okay. At this point, Q is equal to K, so nothing changes with time. However, let's add something in. Okay, let's add in some NO2 at this point. Okay, we're adding in NO2 at this point. That means that immediately the concentration of NO2 will go up. So at this point, since we're adding NO2, that means that Q now is greater than K. And this will slowly start to slope back down to reach a new concentration, new equilibrium concentration that's different than the first. And the N2O4 during this phase will also slowly increase to reach a new concentration. Okay, so then at this point here, we'll say, whoa, really bad. Oh no! We'll say at that point there, we are at equilibrium. And now Q is equal to K again. So this system is responding to the change by using up excess NO2 and producing more N2O4. Okay, so that the final concentrations that you're at are higher than the initial, but the system is responding to that change. Now let's look at the opposite. What happens when you add, what happens when you add in N2O4? So again, we have concentration on the y-axis, we have time on the x-axis, and we'll have our same concentration starting out, NO2 and N2O4. Okay, but in this case, we're adding N2O4 at this point. So we're going to spike N2O4 concentration. Well, maybe I shouldn't go down that much. Something like that. Okay, so we're going to spike the N2O4 concentration. And because of this, we're going to start slowly creating NO2. Okay, so in the end, we have some equilibrium expression, or equilibrium of the system. Here we added N2O4. Q, in this case, is less than K. And then after we reach equilibrium again, Q is now equal to K. But we have a different initial concentrations of NO2 and N2O4. So disturbing the system increases or decreases the concentration of each of the substituents in this case. However, the equilibrium will be re-established due to that Le Chatelier's principle. The equilibrium will re-equilibrate to new values. Okay, and it all depends on Q. If Q is less than K, the reaction is going to shift right. And if Q is greater than K, the reaction is going to shift left. Okay, that's concentration. Now, let's look at what happens when we change the pressure or the volume. What happens when we change the pressure or the volume? If we look at, let's say, a system in a piston. Okay, we have a piston within a cylinder, and we can move this piston up and down to change the volume in the canister below. And when we decrease the volume, ostensibly, we're also increasing the pressure due to the ideal gas laws. Pressure is inversely proportional to volume. So if we have some reaction that's happening down in this part of the vessel, let's say we have a reaction between nitrogen gas and hydrogen gas to produce ammonia gas. On this side of the equation, we have 4 moles total. And on this side of the equation, we have 2 moles total. Let's say that we push the piston down. So we're decreasing the volume and we're increasing the pressure. So pressure goes up, volume goes down. What happens to this equilibrium? If we have some sort of equilibrium happening within this vessel and then we suddenly increase the pressure, how can the chemical system respond? Okay, how can the chemical system respond? How does it respond? So it wants to reduce the pressure to get back to equilibrium. So it wants to reduce that extra pressure and get back to equilibrium. How can it do this? How can it reduce that pressure? Remember the ideal gas law. PV is equal to nRT. An important piece of this, at least in relationship to this system that we have up here, is that pressure is directly proportional to the number of moles. Okay? Since pressure is directly proportional to the number of moles, we can look at the number of moles that each side of the reaction have. So the reactants has, 2 moles? And the products, oh no, sorry, I'm backwards. Reactants have 4 moles. The products have 2 moles. Right? Since pressure is proportional to N, which direction do you think this reaction would go in to reduce the extra pressure? If you said it's going to go to the right to reduce the pressure, you would be right. Because remember, pressure is proportional to the number of moles. So in a case where you're increasing the pressure of a system, the reaction will go towards the direction of lowest number of moles. So in this case, the reaction shifts towards the right. Which is the smallest number of moles in the reaction. Okay? Now, opposite. What happens when you do the opposite? Conversely, if you pull the piston up, okay? If you pull the piston up, you will increase the volume and thus decrease the pressure. When you're decreasing the pressure, the reaction wants to equilibrate or wants to respond to that by shifting towards the highest number of moles. It wants to increase the pressure because you're decreasing it more than it wants. Okay? Since P is still proportional to N no matter what you do, okay? Pressure is always going to be proportional to N. In this case, the reaction shifts to the left, towards the largest number of moles. Okay? So if you have an increase in pressure or a decrease in volume, the reaction shifts to smallest number of moles. And if you have a decrease in pressure or an increase in volume, the reaction shifts to the largest number of moles. Okay? So that's what happens in a system when you have something that pressurizes or depressurizes a system. Sometimes, though, you have a reaction that has the same number of moles on both sides. This is not an uncommon thing. You can always have a reaction. Whoa, my what drawing skills are bad today. What happens if number of moles is equal on both sides? Okay. For example, if we go from 2A plus C goes to 3B, we have 3 moles on both sides of this equation. What happens when you change the pressure? If you increase the pressure, nothing happens. If you decrease the pressure, nothing happens. Okay? The system cannot respond. The system can't respond to this, so it doesn't. And as a matter of fact, the equilibrium itself doesn't change at all. Okay, so that's pressure. Let's see what happens when we change the temperature. What happens when we change the temperature? So what we've looked at already is for concentration and pressure changes. So for C and P changes, K has always remained constant. Okay, K has remained constant. Wow, that's a really bad remain. Let me rewrite that. Okay, for C and P changes, or for concentration and pressure changes, K remains constant. But when we have a change in T, we have a change in K. Yikes, what are we going to do now? Okay, when there is a temperature increase, let's come up with a way of dealing with this, because this is a little tricky, right? We haven't come to a point yet where the equilibrium constant is changing. We've always just assumed that it's going to be constant for the reaction. But since it's proportional to the temperature, when you change the temperature, necessarily the equilibrium constant will change. So we have to take care of that, and we can. Okay, so if we have a temperature increase, the reaction will always shift to decrease the temperature. Okay, it's always going to shift to decrease the temperature that is going on here. Okay, so if you have an exothermic reaction, if you have an exothermic reaction, say for example, A plus B is going to C plus D plus heat. Okay, that means that the reaction in this case is going to shift to the left. And actually, it's better to talk about heat in this case and not temperature. Okay, so the reaction shifts to decrease the heat. If you have an endothermic reaction, so for example, you need heat as a reactant, and you increase the temperature, the reaction will shift to the right. Okay. If you think of heat as a reactant or a product, then the use of the Le Chatelier's principle actually makes sense here, because if you're increasing the temperature, right, you're increasing the amount of heat that's available, right? So you have excess heat in the system. When you have excess heat in the system, if you treat it just like a chemical and just like a product in this case, it makes a lot of sense that the reaction is going to shift to the left to get away from that heat, or to dissipate that heat in some way. Now, if you think of it from the perspective of needing heat as a reactant, and you add extra heat into the system, of course the system is going to use that heat to produce more products. Okay? And of course, the opposite is true with a temperature decrease. With a temperature decrease, if you have an exothermic reaction, the reaction shifts to the right. to produce more heat, basically. And in the case of an endothermic reaction, the reaction would shift to the left with a temperature decrease. Okay, actually, believe it or not, that is chapter 15. We are finished. Please, please, please make sure to go through the chapter itself, read the chapter, do the example problems. The example problems in this chapter are really quite good, and they will walk you through all of the intricacies of solving these complicated equilibria problems. Okay, so I highly recommend you do that. I've posted the homework, and I've also posted a Jamboard, and that's going to be due next week, or next Monday. So be sure you get a jump on that and start working towards finishing chapter 15 homework. Okay, that's it for me this week. Not this week. I'll see you guys on Wednesday. I hope you have a great day. Here in East Tennessee, the weather is absolutely amazing today. And so I think I'm going to go outside and kind of just enjoy the sun. And I recommend that you guys do the same if you're in an area that has nice weather right now. All right? Get some of that vitamin D. All right. Talk to you guys on Wednesday.